All right, so I'm just gonna go through the problems from the problems I wrote for the first lecture. Kind of briefly, the solutions are pretty comprehensive, but this is mainly just for the visual things that the solutions can't convey very well. So starting with problem one, we want to just find a general formula for the magnitude and direction of a vector. Recall that this right here, sorry, this right here is how we write our is our just our standard notation for vectors. That's the column vector. And these two components are separate. So this Vx represents the x components, and that's literally just where on an x coordinate plane our vector is, or where on the x axis our vector is. And Vy represents where on the y axis our vector is. So if we just draw it like that, then our vector is going to look something like this, where you have a triangle made of Vx and Vy. This height right here is Vy. This height right here is Vx. Now, oh my God. So this is Vx. We know that this is a right angle because the y-axis is perpendicular to the x-axis. So the length right here is going to be the square root of v squared x plus v squared y. And that's actually just equal to the magnitude of v itself. It's as simple as that. That's just the size of the vector. So that makes sense if you think about it. We're talking about the magnitude as in how large the vector is should be just the length of that vector. One thing I want to point out here is that I can translate this vector anywhere on that coordinate plane. I could have drawn this vector right here, and as long as it's the same length and points in the exact same direction, it's the same vector, right? Because a vector is fully specified by its magnitude and direction. And then the direction, I mean, it's just given by this right here divided by this right there divided by this right there. And yeah, so that's it for problem one. So for this next question, you're given that the magnitude of the vector is 7 and that it points pi over 4 above the positive x-axis. So we obviously are going to start by drawing it out on a coordinate plane. We know it's 7, so I was going to draw some arbitrary length, and this is going to be equal to 7. And we know that the angle it makes with the x-axis right here is pi over 4. So we have an angle and we have a length. And let's do some trigonometry to find this length right here. I'll use a different color for that actually. To find this length right there, and to find this length right here. So green is going to be our Vx, and blue is going to be our Vy. So sine of pi over 4, or that angle, is going to be opposite over hypotenuse, which equals Vy over 7. Cosine of pi over 4, sorry, yeah, cosine of pi over 4 equals Vx over 7. These two, you should remember from just basic trig that they're equal to 1 over root 2. So we have 1 over root 2 equals Vy over 7, which equals Vx over 7. So you can see that Vy and Vx are going to be equal to each other, and Vx equals Vy, which equals 7 over root 2. And so our final answer for V is going to be 7 over root 2, 7 over root 2. And that's all there is to that one. The point of this question is just to get you familiar with that kind of trig manipulation. I know the first time I saw that in like my physics 1 class, I was a little like, oh, that's a little surprising. And so it's good to see how that's done. And yeah, that's it for problem 2. So for this next one, I asked you to show that, oh, I asked you to show that the vector I hat, which equals 1, 0, is linearly independent from the vector j hat, which equals 0, 1. So when I say linearly independent, that means I can't, if I pick some number, we'll call it gamma. If I pick some number gamma, I can't find any gamma times I hat that equals j hat. There's no real number gamma that satisfies that. And if we think about this, whatever gamma I hat is equal to gamma 0. And so for this to be equal to that, I'd need gamma to be equal to 0 for this first entry to be the same. But if gamma is equal to 0, the bottom entry is not going to be the same. In fact, no matter what you choose for gamma, the bottom entry is not going to be the same. And geometrically, this makes sense. If we think about what multiplying does here, I hat looks like this. Oops. I hat looks like this. And multiplying by a scalar gamma, you can get to here, you can get to here, but you can't move along the axis on which j hat lies. This is j hat. And there's no way to multiply I hat by anything to get j hat. So these two vectors are linearly independent. And that's it for problem 3. So for this next one, before getting into the question, I want to briefly describe linear dependence and independence in like a mathematical way. If I have a set of n vectors, here I wrote the dot 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 to represent you can put as many vectors as you want. And you can come up with whatever numbers A, B, whatever else, C, times each of those vectors and you add them together, or a linear combination of all those vectors that's equal to 0, where not all of your constants are equal to 0. Because obviously if I do 0 times v1 plus 0 times v2 plus 0 times v3, I can get it to equal 0. But if I can do even just one of them that isn't 0, then the whole set will be linearly dependent. One implication of that, if you're thinking about it, is that if the 0 vector is one of our vectors, then the set will always be dependent. That's not so important here, but that's one implication. So I'm asking, is it impossible to have a 2D linearly independent set with 3 vectors? In other words, if I want to find, are there A v1 plus B v2 plus C v3 equals 0, where each v sub n is some vector with alpha and beta, where alpha and beta are also just numbers. So suppose v1 and v2 are linearly independent. In other words, v1 is not a linear combination of v2. We just showed that I can take any multiplier on this first vector, say v1 equals 7 and 3, and v2 equals 3 and 7. And then we'll say v3 just equals alpha and beta. I can choose v1 so that my multiplier on v1 gives me alpha, right? So I'll do this. v1 gives you alpha. Then I can choose v2 so that oh sorry, let me rephrase that. I can choose, I can just create a system of equations where there's 2 equations, right? Where v1 times the constant in front of v1, we'll say that's A, and v2 times the constant in front of v2, we'll say that's B, gives us v3. So 7A plus 3B equals alpha. That comes from this one and this one. And then I'll use a different color here. 3A plus 7B equals beta. That comes from this one, and this one. Now, logically, and you should know this from algebra, if you have 2 equations that they aren't the same equation, and they're not like disagreeing and saying like 0 equals 1 or something, then you're gonna have a solution. In fact, you exactly determined one solution. This speaks to a deeper thing from linear algebra about rank and some stuff that we're not going to go into. But the big idea is this. I have 2 equations that are different, and they perfectly specify a value for A and B that will give me a solution to this equation to create V3 from V1 and V2. We made no assumptions about the values for v1 and v2. Really, I can choose whatever numbers I want within these two vectors, and as long as v1, oh, sorry, as long as v1 does not equal some multiple of v2 in two dimensions, then I'm guaranteed that I can make v3 from those two, and so the set will be dependent. In general, in n-dimensional space, the maximum number of linearly independent vectors you can have in a set for the set to still be linear, or sorry, the maximum number of linearly independent vectors you can have is n, and we call that a basis. You need n vectors in a basis for n-dimensional space to be able to create any vector in that n-dimensional space. And you can look up that more. You can also talk about the span of those n vectors within the basis. That is the space itself, but that's not really relevant here. The main idea is this, that you need n vectors in n dimensions to be you need n linearly independent vectors in n dimensions to be able to create any vector within that n-dimensional space. All right, for this next one, I want to find a general way to calculate v1 dot v2. Because remember, this is equal to the magnitude of v1 times the magnitude of v2 times the cosine of the angle between them by definition, but that's a little clunky to work with. That doesn't really lend itself to a easy calculation of this. So we remember that the dot product obeys the distributive property. This is given to you, I guess, as a fact. I didn't really prove it for you guys, but it follows from just properties of linearity of the dot product and the fact that we're working in, I mean, linear algebra. We're going to deal with linear operations like the dot product. There's much deeper explanations than that that you can find elsewhere. Anyways, so we want to find a I hat plus b j hat, that's v1, dotted with c I hat plus d j hat, that's v2. So let's use the distributive property and so we get a I hat dot c I hat plus a I hat dot d j hat plus b j hat dot c I hat plus b j hat dot d j hat. Okay, so now let's take a step back from this kind of big equation and look at what we're really saying here. First of all, we have this term right here and this term right here are dot products of I hat with j hat. And if you remember what a dot product says, it's the amount of one vector that's in the direction of the other. But for I hat and j hat, those two vectors are perpendicular. None of the first vector, none of I hat is in the direction of j hat. So this term goes away. This term also goes away for the same reasoning. So we're left with ai hat dot ci hat plus bj hat dot dj hat. And I hat and I hat, those are the same vector. They're in the same direction as each other. So this is just going to be equal to AC, and this is just going to be equal to BD plus BD. In other words, V1 dot V2 is equal to AC plus BD. And if we write out V1 and V2 in column vector form, it actually becomes a lot more obvious what this is really saying. V2 equals CD. We're saying you multiply the corresponding components of each vector that you're dot producting together and then add up each of those results. So in red, I'll write this first in green actually. Take A and C, A times C, and then plus take B and D because those are the same. Those are the same component, B and D, to get this. And that's all there is to it. That is, to be clear, not how the dot product is defined. That is a convenient way to calculate the dot product that you'll use very, very often. But really, the definition of the dot product is like a lot more useful than it seems. A lot of the time you'll calculate vector projections and you'll calculate angles between vectors using this formula in disguise. And in fact, later in this, in fact, in the next question actually, we'll use this very formula to show how you arrive at the determinant. Okay, so more so than talking about the determinants here and how to calculate determinants, I'll address that more in the next question. I want to address the fact that we're trying to find the area of this parallelogram and how we go about doing that. Because, sorry, this should be V2. Wrote something wrong. This should be V2, and this should be V1. This is vector 1. This is vector 2. I'm gonna see that. It's vector 2. So, because it's a pretty interesting derivation, I think. So, and the reason it's interesting is because the magnitude of their cross product is of course equal to A. So remember that the area of a parallelogram is the exact same as the area of a rectangle, base times height. And if you wanted to like show that visually, if you take this line right here, translate this this triangle right here, and you can see you're left with a rectangle with the base times height. However, finding the height is not as easy as in rectangle because it's not directly given to us. And to be clear, the height is this. It's what's perpendicular to this base and leads up to this vertex right here. So the way we're going to do that is we're first going to and I'm going to erase this red because it's actually not relevant. It's just showing like what that top vertex is. So I'm going to erase that. We're going to let the angle between V1 and V2 be theta. Okay? From trigonometry, and we're going to let this height be h. From trigonometry, we have that sine of theta equals h over that length of V2, which is just magnitude of V2. Okay? So h equals V2, or magnitude of V2 sine theta. The area of a parallelogram is given by the length of the base, which here is V1 times h, which is going to be V2 sine theta. That's our area. But this formula is not the determinant, which what we're looking for is something that looks like AD minus BC. How do we incorporate our A's and B's and C's and D's into here? I could say V1 equals square root of A squared plus B squared, V2 equals square root of C squared plus D squared, and then we have A's, B's, C's, and D's. And I could do some more math to find the the value of theta in terms of A, B, C, and D. But there's a better way to go about this. We know that cosine of pi over 2 minus theta equals sine of theta. You should know this as a trigonometric identity. It's not too hard to prove either. There's a million ways you can go about it. Um, so A is also equal to magnitude of V1 times magnitude of V2 times cosine of pi over 2 minus theta. So, observation number 1. This looks a lot like our dot product definition. And observation number 2 is that the angle pi over 2 minus theta is this angle right here. That's pi over 2 minus theta because this angle right here is pi over 2. This angle is theta, and we're in a triangle. So pi over 2 plus this equals 180, and you can see from there how we end up with this being pi over 2 minus theta. So we're taking the dot product of this vector right here with, or really, it doesn't matter which way I point it, but we'll say it that way, with this vector right here. Okay? I really should point it the other way, but we're taking the dot product of this vector with this vector. And this vector is going to be given by negative B A. And if you remember from your like just some, I guess this would be what, geometry. If you have y equals mx plus b, all lines perpendicular to this will have slope -1 over m. And if you do some math trying to express this in standard form with ax plus by equals c, you'll see that this is the same thing as saying negative bx plus ay equals some other c. That's how we end up with the perpendicular line. But that's for you to show it to yourself on your own. So there's a couple ways you can prove that, but for now, I'm just going to accept this as a fact that negative b over a is perpendicular. And so this last step is going to be negative b a dot product with c d equals negative b c plus a d, which equals a d minus b c. And this is also equal to, I'll just write this out for clarity, the determinant of the matrix A, B, C, D. And you can remember that because we just cross, oops, you cross this term and then subtract by this term. That's how I remember the 2 by 2 determinant. AD minus BC. So for the 3 by 3 determinants, I'll just very, very briefly say how to do this. If I have a matrix given with A, B, C, D, E, F, G, H, I, the way we calculate the 3 by 3 determinant is pick any row or any column. I'm going to pick the top row for convenience. You don't have to, and you can also pick columns. And that's because of the transpose properties with the determinants. Not relevant here. So I'm going to pick this top column. And then you're going to go for each term. Start with A, and we're going to say A times the determinant of the terms that are not in the same row or column as A, which are going to be these terms. A times the determinant of E, sorry, with determinants, you normally just use a vertical bar, E, F, H, I. Then we're going to subtract this one minus B times the determinant of D, F, G, I, because those are the terms that are not in the same rows or columns as B. And then plus C times the determinant of D, E, G, H. D, E, G, H. And you can, and then these 2 by 2 determinants we just showed how to evaluate. So that's called cofactor expansion. Each one of these guys is a cofactor. And the reason there's a plus minus there relates to the fact that I can swap rows and swap columns to have the same determinant, or I mean, more deep mathematical facts, I guess. But the plus and minuses are not arbitrary, and they're assigned by this just matrix checkerboard kind of thing of pluses and minuses. And this extends all the way out however many rows and columns you want. So if I were to choose the second row instead of the first row, I wanted to do D, E, and F, it would be negative D times determinant of whatever plus E times determinant of whatever minus F times determinant of whatever. And once again, you can also use columns. Now, let me erase all that just so I can show one thing with this. From the last question, remember that I said the magnitude of the cross product is the same as the area of the parallelogram, which is the same as this determinant of A, B, C, D. Let's let our vector v1 equal A, B, 0, and our vector v2 equal C, D, 0. Okay? Now I'm just saying these two vectors lie in the plane. It's the exact same setup as the previous question with the parallelogram, actually, but I'm saying now there's a z component, but that z component is 0. If we set up our matrix like I said to for the cross product with I hat, J hat, K hat, A, B, 0, C, D, 0, and we calculate our determinants using the top row, we're going to say I hat has the determinant of A, 0, sorry, A0, C0, because, sorry, that's, should be I hat times the determinant of B0, D0, minus J hat times the determinant of A0, C0, plus K hat V1 cross V2 equals the determinant for this, plus K hat has the determinant of A, B, C, D. Now, these first two determinants, B times 0 minus D times 0 is 0. This becomes nothing. A times 0 minus C times 0 is 0. This becomes nothing. A times D minus B times C is A times D minus B times C. And so our final vector is equal to AD minus BC in the direction of K hat. And the magnitude of this vector is just going to be AD minus BC. So this is a proof of concept. Our determinant thing works, and it still gets us and still gives us a magnitude of the cross product equal to the 2 by 2 determinant for the same parallelogram. And that is the result that we should get for this question. So this next question addresses eigenvalues of a matrix. And so briefly, I'm just gonna show how to set up the math here. So I gave you the matrix, it's like one of the few times I'll give you actual numbers to work with, but I gave you the matrix A, which equals 1, 4, 3, 2. I kind of just arbitrarily selected these numbers so that the final answers look kind of nice. And so to find the characteristic polynomial of the eigenvalues, which is just how we solve for the eigenvalues, we need to find an f of lambda that equals the determinant of A minus lambda times the identity matrix. And remember that the identity matrix I is equal to 1, 0, 0, 1. It's the equivalent of subtracting 1 or multiplying by, I mean, it's the equivalent to like the single number 1, except for a matrix. So this determinant is going to be equal to the determinant of the determinant of 1 minus lambda, 4, 3, 2 minus lambda, which equals 1, 1 minus lambda times 2 minus lambda minus 12, which if you just do the algebraic simplification, this is equal to lambda minus, and then you do the simplification and then you factor, which I show in the notes, lambda minus 5 times lambda plus 2. So the values of lambda that solve this, if I want f of this to equal 0 for the eigenvalues, which is how we solve the eigenvalues, we want this f of lambda to equal 0, means our eigenvalues are lambda equals 5 and lambda equals -2. So I'm saying that there exists A times a vector v that equals 5 times that same vector v. Let's say v equals uh, x and y. Okay? Then I'm saying A times v, A times v then equals another vector, but I'm not going to write this as a vector. Instead, I'm going to go and write this as a system of equations. So A times V, that first entry in it is going to give us 1 times X. I'll write out A again here. 1, 4, 3, 2. And remember the way I said that you can write out matrix multiplication. 1 times X plus 4 times Y. So X plus 4Y equals 5 times the first entry there. So 5X. And then 3 times X plus 2 times Y equals 5y. Both these equations are saying x equals y. And so any vector v that satisfies x equals y is an eigenvector for the eigenvalue 5. And you can verify. Let's just choose like, I don't know, 7, 7 equals v. Then a times v equals 7 plus 4 times 7, which equals 35. And then the bottom one's going to be 3 times 7 plus 2 times 7, which equals 35. And 35 is 5 times 7. So that makes sense. We do the same process for the -2 eigenvalue. I'm not going to show the steps because that just takes a bit of time, but you'll end up with, if you solve your system of equations, the eigenvalue for lambda equals -2, eigenvector for lambda equals -2 is -4, 3. So that is how we solve for the eigenvectors and eigenvalues here. Really, I have not found myself doing this process by hand much in physics because we have tools like Mathematica that can solve for eigenvalues. This is probably the simplest eigenvalue case I could give. And really they get quite nasty because you have to take 3 by 3 determinants, you have to take larger determinants than that, you have to solve polynomials of high degrees, and at a certain point it's just faster to do it with a computer, which is not a bad thing. But just though really I want to emphasize, if you just understand that an eigenvalue says a v hat equals lambda, sorry, a times the vector v equals lambda times the same vector where lambda is a number, that's the most important thing. This is like the most useful part of linear algebra, that we have things that look like this, and that things that look like this have very nice properties. Okay, last but not least, I'm going to talk about matrix multiplication, and these two properties. I say that the first one, AB equals BA, is not generally true. However, A times B times a vector always equals AB times that vector, assuming the matrix multiplication is compatible. Um, I'll just once, rather than like going through the actual questions here, you can find examples really easily to support these. I'm just gonna show a matrix multiplication example of two 2 by 2s, 2, 4, 1, 2 times 1, 2, 3, 4. In other words, I'm saying A equals 2, 4, 1, 2. B equals 1, 2, 1, 2, 3, 4. And I want to find AB. So I wrote it like this because this is how I remember how to do matrix multiplication, but really what I'm doing is multiplying all the rows in A by the columns in B. So starting with row 1 of A and column 1 of B, which I'll do in red. 1 times 2 equals 2, plus 3 times 4 equals 12. That's going to be equal to 14. Now, the next one, we take the second row of A times the first column of B. And so we're going to do 1 times 1 equals 1, plus 2 times 3 equals 6. That's going to be 7. Then we take the first row of A times the second column of B, which is going to be 2 times 2, which is 4, plus 4 times 4, which is 16. It's going to be 20. And then running out of colors, uh, purple, I guess. I'm going to take the second row of A times the second column of B to get 1 times 2 is 2, plus 2 times 4 is 8. So 2 plus 8 equals 10. And so our final matrix is going to be equal to 14 in the first, in the 1, 1 entry. Then for the second row first column, because which we get from the second row of A and the first column of B, we're going to have 7. Then for the first row second column, we're going to have 20. And for the second row second column, we're going to have 10. And this is equal to AB. And if you do the math to find BA, you can actually, for even this example right here, see that AB is not equal to BA. Matrix multiplication is in general not commutative, which makes sense. Because if I swapped these two, I'd instead be taking the columns of A with the rows of B, which is a completely different mathematical situation. It's not obvious that it would be equal, and in fact they aren't equal. So for the second property right here, it's just I would recommend just choosing like A, B, C, D for A, and then for B you choose D, E, F, G. That's like the most intense, I guess, way to prove it. And it's a good practice with matrix multiplication to show that this is true. And then you can let V equal Vx, Vy, and you'll see that these two are equal. So that's it for this week's problems. Once again, these are rather abstract and it's not very apparent why these are applicable to physics, but these concepts will just come up so much and they come up in combination with other things. So it's hard to really find physical situations where you're using just these concepts on their own. Although, I mean, I could, like force diagrams, and if you take AP Physics 1, that the entirety of Unit 1 and Unit 2 really is just vectors. So that's it. Thank you for um,